Subtopic 7.1 Acids and Bases. Learning outcomes. 1. Define strong acid and strong base, weak acid and weak base, pH, pOH and pKw. 2. Relate pH and pOH to the ionic product of water Kw at 25 degrees Celsius. 3. Calculate the pH values of a strong acid and strong base. Strong acid. Strong acid is an acid that dissociates completely into ions in water. For instance, nitric acid plus water produces nitrate ion and hydronium ion. In this chemical equation, we use single arrow to indicate a complete dissociation of an acid. Strong base. Strong base is a base that dissociates completely into ions in water. For instance, sodium hydroxide dissociates into sodium ion and hydroxide ion. In this equation, we use single arrow to indicate a complete dissociation of a base. Let's have a look at this picture. The bar graphs show the relative numbers of moles of species before and after dissociation. As we can see here, a complete dissociation means no nitric acid molecules present after dissociation, because it has been completely dissociated into hydronium ion and nitrate ion. Weak acid. Weak acid dissociates slightly into ions in water. For example, HCN plus water produces Cn- and H3O+. For this equation, we use reversible arrow to indicate a slight dissociation of an acid. Weak base. Weak base dissociates slightly into ions in water. For example, ammonia plus water produces ammonium ion and hydroxide ion. We also use reversible arrow to indicate a slight dissociation of a base. This picture defines the meaning of slight dissociation. After dissociation, a large amount of HCN molecules remain intact, while a very small amount of hydronium ion and cyanide ion has been produced. pH. The pH is defined as the negative logarithm log of hydronium ion concentration. The formula is written as pH equals a negative log concentration hydronium ion or concentration of proton. pOH. The pOH is defined as the negative logarithm log of hydroxide ion concentration. The formula is written as pOH equals negative log concentration hydroxide ion. Auto-ionization of water. Water can act as Bronsted lauric acid or Bronsted lauric base. Water dissociates very slightly into ions in an equilibrium process called auto-ionization of water. The equilibrium constant for this process is expressed as Kc equals concentration of hydronium ions times concentration of hydroxide ions divided by concentration of water molecule to the power of 2. Since the degree of dissociation of water is extremely small, concentration of water is assumed as a constant. We write the equation Kc equals concentration of hydronium ion times concentration of hydroxide ion. Because this expression refers specifically to autoionization of water, Kc has changed to Kw and known as ion product constant for water. Kw equals concentration of hydronium ion times concentration of hydroxide ion. For pure water at 25 degrees Celsius, concentration of hydronium ion is equal to concentration of hydroxide ion, which is equal to 1 exponent negative 7 molar. So from this formula, Kw equals concentration of hydronium ion times concentration of hydroxide ion. We substitute the value into the formula. And finally, we will get Kw equals 1 exponent negative 14 molar squared. The relationship between Kw, pH and pOH at 25 degrees Celsius. From this formula, Kw, we take the negative log on both sides, which results in pKw equals pH plus pOH, and substitute the value into this formula, and finally you will get 14 equals pH plus pOH. Let's try this example. Question: calculate the pH of 0.15 molar of HCl solution. From this question, we know that HCl is a strong acid and 0.15 molar is the initial concentration of the HCl. To find the pH, we must have the concentration of hydronium ion or concentration of the proton. So firstly, we have to write the dissociation equation of a strong acid HCl. HCl dissociate produces a proton and chloride ion. So on the left side, write the initial concentration slash molar, which is the unit of the concentration, and concentration final slash molar. Initial concentration for HCl is given in the question, which is 0.15. And the concentration for proton and chloride ion are both 0 because initially they are not produced yet. For final concentration, since HCl is a strong acid and completely dissociated, so the final concentration for HCl is 0, and concentration for proton and chloride ion are the same as the concentration of HCl, which is 0.15. So now we have the concentration of the proton, so we can use the formula of pH. So pH is equal to negative log concentration of proton. Substitute the value into the formula, and finally you get the pH is equal to 0.82. Next, let's try the second example. Question: calculate the pH of 0.05 molar of sodium hydroxide solution. From the question, sodium hydroxide is a strong base, and 0.05 molar is the initial concentration of sodium hydroxide. And again, to find the pH, we must find the concentration of proton or concentration of hydronium. So for this question, we start with dissociation equation of sodium hydroxide. Produces sodium ion and hydroxide ion. Same, on the left side, we write the concentration initial slash molar and the concentration final slash molar. So initial concentration of sodium hydroxide as given in the question, which is 0.05 molar, and sodium ion and hydroxide ion both are 0. Same as acid in the previous slide, sodium hydroxide final concentration is 0, and after dissociation, sodium ion and hydroxide ion have the same concentration as sodium hydroxide, which is 0.05. So now we have the concentration of hydroxide ion, so we can use the formula of pOH equal to negative log concentration hydroxide ion. Substitute the value into the formula and the pOH is equal to 1.3. So to find the pH, we use this formula pH plus pOH equals to 14. Substitute the value of pOH into the formula and we get the pH is equal to 12.7. That's all. Thank you.